I'm starting a new series that I'm going to call Physics in 24 Problems. I made that up and I counted 24 problems from Halliday and Resnick and Walker that I think are good enough or general enough so that solving that problem we can talk about everything in that particular chapter, and hopefully things will make sense. And if they don't, that's fine. If it's not useful, it's not useful. But what I want to do is to not just solve the problem, but solve the problem kind of from scratch and go over all the details that go along with it. So I'm going to start with this book, Calculus-Based College Physics, one of the more popular ones, not the best, just popular. And I picked a problem from chapter 2 that I'm going to start with. So chapter 2 is motion along a straight line, and I'm going to do problem 100, and I'll tell you what it is, and then we'll talk about the physics, and then we'll solve the problem. Okay, maybe it'll be fun, maybe not. So the problem states a parachutist bails out, I'm not sure why, they usually just jump out, and falls 50 meters free fall, so no air resistance, and then pulls open the parachute, so it has a deceleration, don't like that word, of 2 meters per second squared, and reaches the ground at a speed of 3 meters per second. And I assume they decelerate the whole way, don't know. And so the question was how high and how long were they in the air? So we're going to solve that problem, but to solve that problem, we need to talk about motion in a straight line. Okay, let's get to it. I got a little tangled up there. Okay. So the first thing we need is position. Suppose I have a person right there. I can describe their position with the value x. And physics is all about describing, not all of physics, but a lot of physics is about describing motions. So knowing where a person is very useful, but that doesn't really make sense because I'd have to know if I give the x value of a person, you don't know where they are, right? Because you don't know where I'm measuring from. So it's not completely unique to say what their x value is. However, if that person moves over here, so let's call this x1, and they move over here to x2, then I can describe a displacement. Delta x is x2 minus x1. That's how they moved. Okay, and we're going to do this as a vector later on, but for now we're just using scalar values, and we'll talk about vectors later. I can also record the amount of time the person was there. So from t1 to t2, I can say the change in time is t2 minus t1. Now with that, I can define what we call the average velocity, and that's delta x over delta t, or x2 minus x1 over delta t. That's kind of important. Now, imagine that person does a whole bunch of stuff during that time. They move over here, and they move back, and everything like that. I don't know what happened during that whole interval, except they started there and they ended there. And so that's why this is the average velocity. If I let the time interval go very, very, very small, I know that all they could do is go from 1 to 2. So I can take the limit as delta t goes to 0, then of delta x delta t, and that's going to be equal to the derivative of x with respect to t, which we call the velocity, the instantaneous velocity. And again, this is in one dimension, so we're writing it as a scalar value. We don't need to use derivatives here, okay, but we're going to. I'm going to show you the kinematic equations two different ways. Now, other than just velocity and average velocity, we also have another term called the average acceleration, or we'll just say acceleration for now because we're not really going to change it. The acceleration we define as the change in velocity with respect to time. So this tells us how the velocity changes. And again, if you take the limit as delta t goes to 0, you get the instantaneous acceleration, which is dv dt, the derivative of the velocity. But the velocity is the derivative of position, so this is really the second derivative of x with respect to time. Okay. Now, how do I describe the position as a function of time if there is an acceleration? That's what we want to do. Okay, I'm going to derive this kinematic equation two ways. I'm going to do it without calculus, and then I'm going to do it with calculus, and then we're going to use it. But already we have one of the kinematic equations. If I look at this equation right here and I solve for x2, I can just say x as a function of time is equal to the initial x plus the velocity, the average velocity technically, average times the time. And so in this case, in this expression, which is useful, x is a function of time, x0 is the position at t equals 0, so delta t is going to be the final t minus the initial t of 0, so we just put it as t. Okay. You could write this as x2 is x1 plus v average delta t, and there's just two ways of thinking about the same thing. Okay, now, but I want to look at the case where there is an acceleration. So I'm going to start with that equation. X is x0 plus v average delta t. I'm sorry, that's not x. X is x0, am I on the board? Yeah. Plus v average times t. And we know that during that time interval, then it's going to go, let's say it starts with some velocity v at time t0 is v0, then, and the final velocity is v, then v average is going to be v plus v0 over 2. Okay, so I can just average the velocity if and only if the acceleration is constant, which is what we're dealing with in this case. So if I put that in up here, I get x is x0 plus v0 over 2 times t. I feel like I'm writing too big, but that's fine. Now, I can actually get an expression for the final velocity. So over here, the acceleration is delta v over delta t, which is v2 minus v1 over delta t. And again, if I use t0 and v0, I get the acceleration is v minus v0 over t. And again, be careful, okay, that is a delta t. It's just that one of the times is 0. And I just want to point that out, because if you write this, v is x over t, if you write a is v over t, you might not be wrong, but you're doing something that's bad. So don't do that. It's very dangerous. And I just want to point that out. It looks dangerous here, but it's not dangerous. And if I solve this for v, I get v equals v0 plus at. Now I can plug that in up here. So I get x equals x0 plus v, which is v0 plus at plus v0, all of that over 2 times t. Let's multiply that out. I get x equals x0 plus, I get v0, actually this is parentheses, times t right there. So I get 2v0 over 2t, which is just v0t. And then I have 1/2 a, and then I have t times t, so 1/2 a t squared. So this is one of your kinematic equations. So that's one of the kinematic equations. Here's one of the kinematic equations. We've got one right there. Now, there is a third kinematic equation. We don't need it, and we can rederive it later in a more simpler terms. But it is possible to eliminate time from this, and we get this equation. V squared is v0 squared plus 2a x minus x0. So you'll see that one too. I just want you to know that it is derivable. I'm not going to derive it, because that's all we need right there. If we know the acceleration, we can find the change in position, and if we can find the change in velocity. Now, one other thing, it doesn't say this in the problem, but if you take a ball and you let it fall with no other forces on it, it will have an acceleration in the y direction of negative g, where g is 9.8 meters per second squared. I think it says that somewhere in the chapter, but we're going to use that. Okay, I think we're ready to solve this problem. Let's just try to make a sketch of the, let's do the velocity as a function of time, because I think that'll be useful. So we have really two sections here, right? We have this right here, and then this right here. So this first part, they're going to start from rest, increase in speed in the negative y direction, and then they're going to decrease in speed in the negative y direction. Oh, there was a thing in there about speed versus velocity, where speed is like the distance per time. But I think that is misused in a lot of different ways. Let's just not worry about that. So suppose I was able to graph the velocity as a function of time. as a function of time. So they're going to start right here, and then they're going to have a negative acceleration over 50 meters, which I don't even know how long that is, but it's going to go like this. And then they're going to have a positive acceleration, because it's deceleration, right? So it's going to be in the positive y direction of 2 meters per second. So that's going to be like this. And so you'll notice the slope of this is negative 9.8. The slope of this is 2. And these are our 2 points right here, right? And we want to know how long that whole thing takes, and we want to know how far they go. So we have, I'm going to call this, let's call this y1, v1, y2, v2, y3, v3. Okay, because I actually don't know this final velocity right there. If I did, I could calculate this time, I could calculate that time, and it'd be pretty easy. So that's the first thing I want to do. I'm going to actually write down a bunch of stuff here. I know y1 is equal to, what did I call y1? Let's call y1, let's call the ground 0. So I don't know what y1 is. I know y, no, I'm gonna not do that. I'm going to say y1 is 0. And so down here, I'm going to have a negative y value, and I want to find for that. And that's fine, okay? But now I can write y2 as negative 50 meters, right? Because they're going to drop down. And then y3, I don't know. I'm trying to solve for that. Over here, I get v1 is the initial velocity of 0 meters per second. v2, I don't know. v3, I do know, of 3 meters per second. T1 is 0, that's where it starts. The time here, T2, I don't know. And then T3, I don't know. So I actually have going from here to there, going from there to there, and that matches that problem right there. Okay, I'm going to start right here and start finding things I don't know. And the first thing I want to find is this velocity right there. Because if I can find that velocity, then I can find the time, which may seem weird. And I'm going to do it, you could do this using that one kinematic equation we don't like, but I'm not going to. I'm going to use, write y2 as a function of time. So if I do that, y2 is y1, I'm calling it y1, plus v1 t minus 1/2 g t squared. And that's going to be the time it takes to go from here to there, which I don't know. Okay. I can also write the final velocity. v2 is v1 minus gt. So I can solve that for time, the second equation, and plug it into the first equation, and I will get what I want, right? Because I don't know, I know v1 is 0, but I don't know v2. So that's 0, that's 0. So I get y2 equals y1, which is 0, minus 1/2 gt squared, and then I can put in t is, yeah, v2 is negative, that's why. T is going to be negative v2 over g. So if I put that in there and square that, I get y2 is going to be equal to negative 1/2 g v2 squared over g squared. So I get y2 is, oh wait. Yeah, I don't know y2. So negative 1/2 v2 squared over g. So let's go ahead and find our value of v2, right? Because I know y2 is negative 50. So I get negative 50 equals negative 1/2 of v2 squared over 9.8. And then if I solve for v2, I get the square root of 100, right? Because that's that multiplied to that, times 9.8. Okay, so let's do that in our handy dandy calculator. Drop. So I have 100. No, I can do that in my head. Why did I do that? 9.8 times, and then I need to take the square root, which is right there. And I get 31.3 meters per second. So over here, that's important. Now I know this. Now I can find that time, right? Here's the time right there. So I can say y2 is negative 50, and that's negative 1/2 g times, this is actually negative. It's plus or minus, right? But I know they're moving down. So negative 31.3 squared. So let's solve. Wait. I need this equation right here, because I know the time now. No, wait, I don't know the time. I'm trying to find the time. Okay, so y2 is going to be negative 50, y1 is 0, v1 is 0, minus 1/2. Oh, I could have done that before. I could have done that either way. No, I didn't know t. No, I do know t. 9.8 t squared. Okay, well, I made it more difficult than it had to be. Sometimes you do that, and that's fine. So I get 100 over 9.8 square root equals t. So 100, enter, 9.8 divided by square root. I get 3.19 seconds. So that's this time right here. Okay, we're moving right along now. I just want to find out how far and how long they take for the second part. So again, I know the acceleration is going to be positive 2 meters per second squared. I know the final velocity, so I can actually find the time. Let's go ahead and find the time. Oh, you know, I said I'd derive that kinematic equation another way, and I didn't do that. I'm going to do that at the end. So if I want to find the time, I can say y3, which I don't know, is I'm going to say this. v3 equals v2 plus a delta t. It's not just t, right? It's technically delta t. And that's the time going from here to there. So let's solve for that delta t. So delta t is going to be equal to delta t is v3 minus v2 over a. So it's going to be v3, which is 3 meters per second, minus v2. Oh, this is actually negative, right? They're moving down. v2 is negative 31.3, negative minus negative 31.3, all of that over the acceleration of 2. So I can get the time. And notice it is a positive number. 31.3, enter, 3 minus 2 divided by 14.15 seconds. That's the change in time. So the total time I have to add to this. But now I have my first answer. So 3.19 plus, I get T3 of 17.34 seconds. Okay, now I want to find my final position. So I can use this equation. Y3 is Y2 plus V2 delta T plus 1/2 A delta T squared. So since I'm not using from time equals 0, I have to use delta T, so I can use Y2, right? And that works with that derivation. I showed you that derivation. That's just fine. So Y3 is going to be Y2, which is negative 50. V2 is going to be negative 31.3. Delta T is that time that I solved right here. It's this 14.5. 14.15 seconds. You can't use t equals 0 because the acceleration is not constant going from there to there. And then I have plus 1/2 A, which was 2. Yeah, 2 times 14.15 squared. So let's put that in the calculator. Drop. 50 negative, I can't see, 31.3, enter, 14.15 times minus, oh, I did that wrong, 50 negative, enter. 31.3 enter. 14.15 times minus 0.5 enter 2 times, I didn't do that. 14.15 squared times, and then that's going to be plus. Yep. And I get negative 292.7 meters. And so that's this final position right here. I mean, it's just tedious. It's not that bad. But I did say I would derive the kinematic equation with calculus. So I'm going to do that now. Okay. So let's start with the definition of acceleration as instantaneous acceleration. A is dv dt. Now, this is a difficult equation to deal with, but if A is constant, I can do the following. I can multiply both sides of the equation by delta t, and I get dv equals A dt. And you might think, whoa, 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 I took math and you can't do that. You totally can. Don't listen to those mean math people. I'm just kidding. Okay. So now I have a term over here that only depends on velocity and a term that only depends on acceleration. I can actually integrate both sides. So if I integrate the integral of dv, I just get v. If I integrate the integral of a dt, I get a t. But I have to have a constant in there too, right? Because I didn't do limits of integration, so I have to include that constant. And let's just call that c. Now I can solve for that constant by saying v at t equals 0 is v0. So if I put in t equals 0 right there, I get v0 equals a times 0 plus c. So c equals v0. So now I have v equals v0 plus at, which is what we had before. Now I'm going to write v as dx dt. So dx dt equals v0 plus at. Again, I'm going to multiply both sides by dt, and I get dx equals v0 dt plus at dt. And now I can integrate both sides. So the integral of dx, I'm going to write this as the integral of v0 plus at dt. So the integral of dx is just x. And the integral of this, I'm going to have a constant times dt. So I get v0t plus 1/2 a t squared using the power rule, plus another constant. Let's just call that constant b now. And if x at time t equals 0 is x0, then I get x0 equals v0 times 0 plus 1/2 a times 0 squared plus b. So b is equal to x0. So if I put that in up here, I get x0 plus v0t plus 1/2 a t squared. Cool? Okay, so that was physics problem number 1 out of 24. I'll make a playlist. The playlist will be in the description down below if you want to see them all. But other than that, that's that. Talk to you later.